So what is an OSPF area? Well, we have just talked about how OSPF exchanges link state advertisements. So if routers are connected in an OSPF domain like this, router 1 will send its link state adverts to router 2 and will send its link state adverts to router 3 too. Router 3 will send its link state adverts to router 2 and will send its link state adverts to router 1. Router 2 will send its link state adverts to router 3 and will send its link state adverts to router 2. Well, this exchange of link state adverts looks to be simple right now, but when we speak of an entire autonomous system that has OSPF routers, there is going to be a problem. So what is an autonomous system? Well, for OSPF, an autonomous system is a collection of IP networks that are under a common administration. So think of Huawei, for example. Huawei Uganda, Huawei Rwanda, Huawei Kenya, Huawei China, Huawei Ghana, Huawei Nigeria. So let us assume this entire Huawei is in one autonomous system. You realize there is going to be too many routers inside that autonomous system. So the autonomous system can be really, really big because it is, as I've said, a collection of IP networks under a common administration, sharing a common routing strategy and running just one routing protocol. In this case, this would be the OSPF autonomous system. If Huawei is also running ISIS, that would be in a different autonomous system. In fact, when you are bringing ISIS routes into OSPF, we'll be bringing external routes as far as OSPF is concerned. Now, routers and links that make up an autonomous system are in logical groups called areas. Why do we do this in OSPF? Well, as I've said, an autonomous system can be really, really large with too many routers, and all of them are running OSPF. So they are going to exchange link state adverts, and the network in between these devices can get really, really messy, can get really, really busy. So OSPF tricks the autonomous system by having the concept of areas. So in a single autonomous system for OSPF can be divided into smaller groups called areas. Now, this reduces the number of link state advertisements and other OSPF traffic that is going to be sent on the network. It also reduces the size of the topology database. It reduces the size of the link state database that each router needs to hold. So let's say an autonomous system has a total of 42 routers. And these 42 routers are divided into 6 areas of 7 routers. Instead of each router of the 42 storing link status databases of all the 42 routers, each will store only for 7 because a link state database needs to be uniform only in the same area. So it reduces the size of the topology database that each router must maintain. The routing devices, therefore, participate in OSPF routing. The routing devices that participate in OSPF routing perform a number of functions depending on where they are in the network. Now, I won't get into the details of that. The idea is that an area is considered to be a logical group, and each group will be identified by an area ID. Now, what's more to this that we need to know? It is true that sometimes you have a small network of routers where we don't need all the many areas, we need just one area. Now, if we need one area, that area can be area 0, can be area 1, can be area 2, can be area 3, and so on and so forth to all the supported area numbers. Area numbers can start from 0, can start from 0.0.0.0 to 0.0.0.1, 0.0.0.2, all the way to 255.255.255. So it means there are 4 billion something supported numbers. An area number can be any of those if it is a single area. However, if there are multiple areas, then one of them must be area 0. Well, we'll talk about this in more detail in a moment. So we define an area by using the keyword area when we are configuring OSPF. Again, we shall see this when we are configuring. That is what an OSPF area is. The other concept I want to make clear is the OSPF router ID. Again, we've mentioned that OSPF routers exchange link state adverts. Well, let us look at this illustration for a moment. When router 3 receives link state adverts from that side and receives other link state adverts from that side, how is router 3 going to identify these link state adverts? That these ones are from router 2 and these ones are from router 1. Clearly, we need some kind of router identifier. So OSPF uses a router ID to uniquely identify a router within an OSPF area. The router ID can be manually specified. If you don't manually specify it, OSPF is going to automatically assign it by the system. Now, you can see in this example, router 1 has the ID 1.1.1.1, router 2 has the ID 2.2.2.2, router 3 has the ID 3.3.3.3. However, in actual projects, OSPF router IDs are manually set for devices. We also advise you to ensure that router IDs of any 2 devices in an OSPF area are different. Generally, a router ID is set the same as the IP address of an interface, like a loopback interface. So in this example, for example, this would be an IP address of a loopback interface, maybe 0, 1.1.1, then we set that as the router ID in order to avoid repetition, because we would have had an IP address in plan already that prevented repetition of IP addresses. When we use that, we are hitting two birds with one stone. So the router ID is going to be automatically assigned by the system if you don't specify one manually, meaning that manually specified router ID is preferred. If there is one which is manually specified, the system will not generate its own router ID to assign it to the router. But if you don't specify one manually, then the system is going to assign its own router ID to each router in the OSPF domain. But where does the system get these router IDs? Well, the system takes IP addresses of interfaces, loopback virtual interfaces, IP addresses of physical interfaces, and so on and so forth. It has its system of selecting the router ID. But the other concept of OSPF that I want us to understand is the cost value. OSPF calculates cost between different devices, between different routers. It costs to specific networks, and it uses the cost as the metric. It uses the cost as the metric of determining how far is the network from me. Each OSPF-enabled interface maintains a cost value. The default cost value is going to be based on the interface bandwidth, and the formula is 100 divided by interface bandwidth in megabits per second. So 100 is the default reference value. Now, sometimes you have much higher bandwidth bandwidths in your network, and you want to modify this reference value of OSPF. So it is configurable. Generally, the cost of an OSPF route is the sum of costs of all inbound interfaces along the path from the destination network segment to the local router. So we have an example here. A fast Ethernet interface has 100 megabits per second. So 100, which is the reference bandwidth, over 100 gives us a cost of 1. So let us look at an interface that has 1,000 megabits per second. 100 reference bandwidth over 1,000 gives us 0.1, but cost cannot be less than 1, so that would be rounded off to 1. Now, a serial interface has 1.544, and if you do 100 divided by 1.544, we are going to get 64 as the cost. But you clearly see it's going to be a problem. We want our cost to be dependent on the bandwidth, but basing on our formula here, if an interface has 100 megabits per second, and an interface that has 1,000 megabits per second, and one that has 10,000 megabits per second, all of them are going to have an OSPF cost of 1. So sometimes we want to adjust the reference bandwidth based on the interfaces we have in our network. Generally, if a network is this far from a particular router, in order to calculate the cost to that network, the router is going to take a summation, it's going to sum together, it's going to take the cumulative cost from that particular network to the local router that is trying to calculate the bandwidth. Again, OSPF uses the cost as the metric. It's the one it uses to say this is how far this network is from me. For example, this router right now is saying this network is 75 away from me. Now, clearly you can see that the higher that value, the poorer the cost, the path. Let us say there is another router here, which is also connected to this network and connected there. So the cost here, let us say, is 40. OSPF will always prefer this cost, this path, to this path, because this is cheaper, it's shorter, it's a shorter distance, it's cheaper it's a cheaper cost I spend to get there than this one of 75. So that is how OSPF uses the cost, and that is how it calculates the cost. Now, as I said earlier, for all these things to happen, of this router determining that there is this router, they are going to exchange their router IDs, they're going to exchange some information, some OSPF packets. So there are a number of OSPF packets that are normally going to be in play if OSPF is to work in between any two routers or any two or more routers in an internetwork. So let us talk briefly about the OSPF packet types. And there are 5 types of OSPF protocol packets that help to implement different functions and interaction between OSPF players or OSPF routers. The very first packet is called the hello packet. And as you might guess, the hello packet is used to discover and maintain neighbor relationships. So if we have a router here connected to another router here, and we configure OSPF and enable it at that interface, configure OSPF on this router and enable it at that interface, this interface will start sending hello, anyone speaking OSPF out there, while this interface is also sending hello, anyone speaking OSPF out there. When these interfaces realize they're both speaking OSPF, they're going to set up a neighbor relationship. And occasionally, as they are still working, they'll be sending a hello packet. Hello, you still there? Hello, you're still there? Just to maintain the neighbor relationship. They don't go silent on themselves for long. The other packet name is the database description, the DD, which describes the summary of the local link state database. We say that after the neighbor relationship is established, OSPF routers will exchange link state advertisements. This guy will get hold of his link state database and send it to that guy. This one also gets hold of his link state database and sends it over to this guy. Well, OSPF uses packets we call database descriptors to exchange the summary of the link state database. It is these summaries that are used to synchronize the link state database of two devices, because when router 2 over here receives the summary from router 1, it checks it and sees which of the entries it doesn't have in its own link state database, and then it sends a link state request to ask for those entries. I hope that makes sense. So what happens once router 1 is connected to router 2 and enable OSPF? First, we are going to use hello packets to form a neighbor relationship. Once we form neighbor relationships, this guy is going to send a database descriptor to that guy to describe in brief a summary, a list of all the link state adverts he has. Meanwhile, this guy will also send a database descriptor to that guy listing a summary of all the link state adverts he has. So when this database descriptor reaches router 2 checks it against its own link state database. Say, I have that one, I have that one, I have this one. Oh, but I do not have this one, I do not have this one, I do not have this one. So what will router 2 do? Router 2 will put together a link state request packet and send it to router 1 and say, wait a sec, can you send me details of this link state advert and this link state advert and this link state? He will send a separate link state request for each link state advert. Now, router 1, on the other hand, will send a link state update, which sends detailed information of a particular link state advert that has been requested through a link state request. When router 2 receives the link state update, it will send a link state acknowledgement saying, yeah, I've received that. I can see all the details now. Please send me the details of the next link state advert. So these are the 5 critical packets that OSPF is going to use. Again, the hello packets are used for discovering and maintaining neighbor relationships. The database descriptor packets are used to share a summary. The database descriptor packets are used to share a summary of the link state database to the neighbor. The link state requests are used to ask for detailed information of entries in the database descriptor that the local router does not know of. The link state update, is used as a reply to the link state request, giving detailed information about a particular link state advert. And the link state acknowledgement is used to tell the sender of the link state update that hey, I received that update. Thanks a lot. Please send me the next link state advert. Again, these are the 5 protocol packets that OSPF uses. Well, with these 5 protocol packets, and speaking of neighbors, speaking of link state databases, speaking of routing tables, you realize there is a number of tables that OSPF needs to keep track of. There are 3 types of OSPF tables. The very first table is the neighbor table. We say OSPF is going to use hello packets to discover neighbors. So in this case, R1 discovers this R2 with router ID 2.2.2.2. R1 has 1.1.1.1. So R1 is going to say, oh, I'm 1.1.1.1. My neighbor is 2.2.2.2. Now, this is going to be some table inside R1, and it's called the OSPF neighbor table. If you want to see the contents of the neighbor table on a particular router, you run the command display OSPF peer in VRP. When you run the command display OSPF peer, for example, in this case on R1, you will see OSPF process 1, and this is R1's router ID, and neighbors is a heading. So in area 0, at that interface, we have neighbor router 2.2.2.2, and the address at router 2.2.2 that is connecting to us is that one. You can see there is a lot of detailed information, some of which we shall make sense of as we go on. The second type of table that is important for OSPF to keep track of, what did we say? After establishing neighbor relationships, we are going to exchange link state adverts and populate the link state database. Means that on router 1, somewhere, it needs to have track of its own link state database. So the second table is the link state database table. The second entry that one OSPF router needs to keep track of is the link state database. So if you want to see the link state database or a particular router that is running OSPF, you run the command display OSPF LSDB, display OSPF link state database. In this example, again, router 1 connects to router 2, they run OSPF, they exchange hello packets, they form neighbor relationships, and so we want to see the link state database of router 1. We'll run the command display OSPF link state database, and it will tell you we're running OSPF process 1 with router ID 1.1.1.1, and in router in this area we have a router link state advert, and another router link state advert, and a network link state advert. So router link state advert has the ID 2.2.2. It was advertised by router 2.2.2. This one has the ID 1.1.1.1. It was advertised by the router 1.1.1.1. It is 98 seconds old. This is 92 seconds old. Its length is 36. This is the sequence. That's the sequence, and that's the metric. So these are link state database entries, which are link state adverts, really. Those are the two first tables. First of all, I said it's the neighbor table, which we get as soon as we become neighbors. We have a list of the neighbors we have. It can be empty, it can have neighbors. The second table is the link state database table. The third table that an OSPF router needs to keep track of is the OSPF routing table. Please note that this is not the local routing table. It's not the routing table you see when you say display IP routing table. It's the routing table you see when you say display OSPF routing. The OSPF routing table and the router routing table are different. So in this example, you want to see the routing table of OSPF. Now, some of these routes will be taken into the local routing table or the local routing information base. Others will not, because they are probably better routes than these ones. But they are all going to be in the OSPF routing table. We shall see this when we run an OSPF lab. Also, for more information about this, you might want to check out our HCIP course. So those are the basic concepts of OSPF. And the next thing we shall be talking about is the OSPF working mechanism. I hope this has been informative for you. Thank you for viewing.